Okay, in this video we're going to go back to estimating an area under a curve. So a long time ago we did this thing called Riemann sums, which helped us, using rectangles to evaluate or to estimate the area under a curve. Then we got into finding the exact area using definite integration. So I'm just going to talk about in this video a different option for estimating the area under a curve. It will give us pretty close approximations, and that's using trapezoids instead of rectangles. So we have this thing called the trapezoidal rule, and it says that if I want to integrate a function from a to b, it's going to be approximately equal to this idea of using the trapezoidal rule. I'm going to show you guys a video in class that explains this in detail, but for the sake of this video, I'm just going to use this rule and make sure that we are all clear on how to use it, but I do want to show you where it comes from, because it's not too difficult to understand how I get this. So I want to estimate this integral using 5 shapes, essentially, whether they be rectangles or trapezoids, and I'm going to do it using the midpoint rule and the trapezoidal rule. So if you remember the midpoint rule, the first thing I would need to do is find my delta x, my change in x, which is going to be the width of each rectangle. I want to go from 1 to 2, and I want 5 of them, so I'm just going to do 2 minus 1, I'm going to divide by 5, which is going to give me 1/5 as my width. Now, if it helps, this is 0.2, right? You should know that. If I'm going to go from 1 to 2, what I'm going to do before I figure out what I need to evaluate and figure out my midpoints, I'm going to figure out what my intervals are. So I'm starting at 1. Each rectangle has a width of 0.2, so I would go from 1 to 1.2, 1.2 to 1.4, 1.4 to 1.6, to 1.8, and to 2. And that would give me 5 equal width rectangles. So if I'm going to use the midpoints, then I would be using exactly in between 1 and 1.2 and so forth. So hopefully that's not too difficult to figure out. So using the midpoint rule, the width of all the rectangles is 1/5, and I'm going to do f of the midpoints. So the midpoint from 1 to 1.2 would be 1.1 to get my height. Midpoint of 1.2 and 1.4 would be 1.3, and then I think you can figure out that it would simply be the odd number in between, 1.7 and 1.9. My function is simply just 1 over x. So I'm going to have 1/5 times 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 and so on, 1 over 1.9. And obviously you would be given a calculator to evaluate this. I wouldn't expect you to do this by hand. But if I take 1/5 times the sum of all of these heights, I get 0.691908. Okay, so that's my estimation using midpoints. And again, the midpoints usually gave us the best estimation with our Riemann sums. Instead of using right or left endpoints, usually the midpoint was the best. So this is probably going to be the best estimate that I have using rectangles. And so let's then see what the trapezoids give us. So I'm going to use this. You're not going to be able to see this on my screen, but I'm going to use this formula. Hopefully you can see it as you're taking notes then, and to where I get this. First thing is, the important part of this is, notice how out front this is just delta x, right? Delta x was 1/5 with midpoints. With the trapezoidal rule, it's delta x divided by 2. So I'm going to have to make sure I divide that by 2. Secondly, my 2 endpoints, I only use those once, and every other point that I'm going to use it twice. I've got 2 in front of all of those. Okay, so keep all that in mind as I work through this. So using trapezoidal rule, again, I'm estimating the same integral using trapezoids. My delta x is still going to be 1/5, but what I want out front is delta x divided by 2. So I'm going to have 1/5 divided by 2 out front. And then it says, again, I'm going to go from 1 to 1.2 to 1.4 to 1.6 to 1.8 to 2. what this says is I'm going to do f of 1, so that's my first endpoint, and then I'm going to have 2 f of 1.2s, 2 f of 1.4, 2 f of 1.6, 2 f of 1.8, and only 1 f of 2. Again, my function is 1 over x, right? F of x is 1 over x. That's what's in the integral. So, first of all, 1/5 divided by 2, that's going to simply be 1/10. F of 1 is simply going to be 1 over 1, so it's just going to be 1. And then I'm going to have 2f of 1.2. So f of 1.2 would be 1 over 1.2, and if I multiply that by 2, I'm going to get 2 over 1.2. And that trend's going to stay the same for the rest of these. 2 over 1.4, 2 over 1.6, 2 over 1.8, and my last one I just have f of 2, so if I plug in 2 I just get 1/2, so plus 1/2. Again, using a calculator, if I evaluate that, multiply by 1/10, I get my estimation here to be 0.695635. So I do have different estimates here. This one is about 0.695 or 0.696, and the estimate using midpoints was 0.692 or close to that. So different estimates. If I were to actually evaluate the integral, so you don't need this, it's not part of the trapezoidal rule, but if I were to actually evaluate from 1 to 2, 1 over x dx, you should know the antiderivative of 1 over x is the natural log of x evaluated from 1 to 2, which is going to be the natural log of 2 minus the natural log of 1. Natural log of 1 is 0, so I just get simply the natural log of 2, and that is 0.693147. So this is the actual area under the curve, and you may ask, why do we need to estimate if I can evaluate the integral? Let's say this function wasn't something that I could integrate easily. I want to be able to estimate. But they were both close. In this case, the trapezoidal rule gave us an overestimate. The 5635 a little bigger than 3147, and the midpoint gave us an underestimate. But they're both pretty close. Okay, so I'm not going to say in general that trapezoidal rule is better than the midpoint rule, or that it's worse. It's just different. It's going to give you a different estimate. Sometimes it may be closer. Using trapezoids, sometimes it may be, a more incorrect answer. So, just another way to do that. You may be asked on the AP test to use the trapezoidal rule. Again, in class, I'm going to show you guys a video of where this trapezoidal rule actually comes from and how we get that formula.